Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Aryabhata the Elder's Aryabhatiyam, composed in 499 Common Era, stands as a monumental achievement in the history of mathematics and astronomy. This compact yet comprehensive work, written in terse verse form, encapsulates the state of Indian astronomical and mathematical knowledge at the cusp of the 6th century. Examining the Aryabhatiyam reveals a sophisticated understanding of arithmetic, algebra, trigonometry, and astronomy, marking a significant leap forward from preceding traditions and influencing generations of scholars in India and beyond. Its enduring impact lies not merely in its collected knowledge, but in its innovative approaches and its challenge to prevailing geocentric models. The intellectual milieu preceding Aryabhata's work witnessed the culmination of centuries of astronomical and mathematical developments. In India, the Sulba Sutras, dating back to the 8th century before Common Era, provided geometric rules for constructing sacrificial altars, implicitly containing early forms of the Pythagorean theorem and approximations of the square root of 2. Jain mathematics, flourishing from the 6th century before Common Era onward, developed large number systems, combinatorial calculations, and explored concepts of infinity. Simultaneously, the Vedanga Jyotisha, a text associated with Vedic rituals, contained early astronomical observations and calendrical calculations. However, these earlier works primarily focused on practical applications related to religious rituals and lacked the systematic, theoretical framework that Aryabhata introduced. The Surya Siddhanta, an astronomical text likely compiled in stages over several centuries, represented a more advanced stage of Indian astronomy, yet its treatment remained descriptive and less mathematically rigorous than the Aryabhatiyam. Aryabhata synthesized and surpassed these earlier traditions, presenting a unified system grounded in mathematical principles. The Aryabhatiyam is structured into 4 sections, known as padas: the Gitikapada, the Ganitapada, the Kalkriyapada, and the Golapada. The Gitikapada introduces the astronomical constants, defines units of time, and presents a unique alphabetic numeral system, allowing the expression of large numbers and astronomical parameters in concise verses. This system, employing consonants and vowels to represent numerical values, facilitated efficient memorization and transmission of astronomical knowledge. The Ganitapada, dedicated to mathematics, covers arithmetic, algebra, plane trigonometry, and spherical trigonometry. Aryabhata provides rules for extracting square roots and cube roots, solving linear equations, and calculating areas and volumes of geometric figures. His approximation of pi, given as 62,832 divided by 20,000, yields a value of 3.1416, remarkably accurate for its time. He also presents the sine table, essential for trigonometric calculations in astronomy. Aryabhata's treatment of indeterminate equations of the first degree, known as Kataka, demonstrates a deep understanding of number theory. The Kalkriyapada deals with units of time, the motions of the planets, and the determination of the true positions of the sun, moon, and planets. Aryabhata proposes that the Earth rotates on its axis, causing the apparent daily motion of the stars, a revolutionary idea that challenged the prevailing geocentric view. He explains the occurrence of eclipses as shadows cast by the Earth and the moon, rejecting mythological explanations. His calculations of the lengths of the year and the day are remarkably accurate for their time, demonstrating the precision of his observational and computational techniques. The Golapada describes the celestial sphere, explains the courses of day and night, and discusses the movement of the celestial bodies on this sphere. Aryabhata describes the ecliptic, the equator, and other important circles on the celestial sphere, providing a framework for understanding the positions and motions of celestial objects. The immediate impact of the Aryabhatiyam materialized in its adoption by subsequent generations of astronomers and mathematicians in India. Aryabhata's disciples, including Bhaskara I and Lala, wrote commentaries on his work, elaborating on his ideas and applying them to practical astronomical calculations. Bhaskara I's commentary, written in 629 Common Era, is particularly valuable for its detailed explanations of Aryabhata's methods and its preservation of earlier astronomical traditions. Brahmagupta, a prominent astronomer of the 7th century, critiqued some of Aryabhata's ideas in his Brahmasyuta Siddhanta, presenting alternative astronomical models and mathematical techniques. Despite his criticisms, Brahmagupta acknowledged Aryabhata's genius and contributed to the development of Indian mathematics and astronomy. The Aryabhatiyam, became a standard text in Indian universities, influencing the curriculum and shaping the training of astronomers and mathematicians for centuries. The Aryabhatiyam also exerted a significant influence on Islamic astronomy and mathematics. During the 8th century, under the patronage of the Abbasid caliphs, numerous Sanskrit texts were translated into Arabic, including the Aryabhatiyam. Al-Khwarizmi, a celebrated mathematician of the 9th century, used Aryabhata's sign table in his astronomical works and acknowledged his contributions to mathematics. Islamic scholars recognized the accuracy of Aryabhata's astronomical parameters and incorporated them into their own astronomical tables. The Arabic numeral system, which originated in India, was instrumental in the development of Islamic mathematics and science, facilitating complex calculations and algebraic manipulations. The transmission of Indian mathematical and astronomical knowledge to the Islamic world played a crucial role in the advancement of science during the Golden Age of Islam, eventually influencing European science during the Renaissance. Aryabhata's heliocentric ideas, though rudimentary compared to later developments, represented an important step towards a more accurate understanding of the solar system. His assertion that the Earth rotates on its axis, a concept that challenged the established geocentric view, anticipated later findings by Copernicus and other European astronomers. It is erroneous to suggest that Aryabhata presented a fully developed heliocentric model comparable to that of Copernicus. Aryabhata's system remained geocentric in its overall framework, placing the Earth at the center of the universe while explaining the daily motion of the stars through the Earth's rotation. Furthermore, Aryabhata's model lacked the detailed planetary orbits and mathematical sophistication of Copernicus' De Revolutionibus Orbium Celestium. Nevertheless, his insight into the Earth's rotation stands as a remarkable achievement, demonstrating his independent thinking and his willingness to question established dogma. One area of critique concerns the limited evidence regarding the direct observational basis of Aryabhata's astronomical parameters. While Aryabhata undoubtedly relied on observations to refine his models, the precise methods and instruments he employed remain speculative. Some scholars argue that Aryabhata may have drawn upon earlier astronomical data and computational techniques, adapting them to his own theoretical framework. His values for astronomical constants, while remarkably accurate, are not entirely consistent with modern measurements, suggesting that they may have been subject to some degree of approximation or theoretical adjustment. Further research into ancient Indian astronomical instruments and observational practices may shed light on this important aspect of Aryabhata's work. Throughout history, the Aryabhatiyam faced both admiration and criticism. Brahmagupta, as mentioned earlier, challenged Aryabhata's heliocentric views and offered alternative astronomical models. Other astronomers and mathematicians, while acknowledging Aryabhata's genius, questioned the accuracy of some of his calculations or proposed alternative methods for solving astronomical problems. These critiques spurred further research and innovation, contributing to the ongoing development of Indian astronomy and mathematics. The Aryabhatiyam served as a catalyst for intellectual debate, stimulating astronomers and mathematicians to refine their theories and improve their computational techniques. The ongoing critical engagement with Aryabhata's work underscores its enduring significance and its role in shaping the trajectory of scientific thought. The methods Aryabhata employed for solving indeterminate equations of the first degree, known as Kataka, are particularly noteworthy. His approach involved a process of successive divisions and remainders, leading to a general solution for equations of the form x plus by equals c, where a, b, and c are integers. This method, known as the Euclidean algorithm, is an important tool in number theory and has applications in cryptography and computer science. Aryabhata's Kataka method demonstrates a sophisticated understanding of number theory and its applications to practical problems, such as determining the dates of astronomical events. His work in this area represents a significant contribution to the development of algebraic techniques in India and beyond. The elegance and efficiency of Aryabhata's Kataka method continue to inspire mathematicians and computer scientists today. The enduring legacy of the Aryabhatiyam resides in its synthesis of mathematical and astronomical knowledge, its innovative approaches to problem solving, and its challenge to prevailing scientific views. Aryabhata's work served as a foundation for subsequent developments in Indian astronomy and mathematics, influencing generations of scholars and shaping the scientific landscape of the region. Its transmission to the Islamic world played a crucial role in the advancement of science during the Golden Age of Islam, eventually influencing European science during the Renaissance. Aryabhata's insightful assertion that the Earth rotates on its axis, while not fully developed, anticipates later findings by Copernicus and other European astronomers and mathematicians. The Aryabhatiyam continues to be studied and admired for its insights, its mathematical rigor, and its enduring contribution to the history of science. Its importance extends beyond its historical context, serving as a testament to the power of human ingenuity and the pursuit of knowledge. In closing, the Aryabhatiyam presents a compelling case study in the evolution of scientific thought. It exemplifies the synthesis of observation, calculation, and theoretical reasoning that drives scientific progress. Aryabhata's work demonstrates the importance of questioning established dogma and seeking new explanations for natural phenomena. While some of Aryabhata's ideas may seem rudimentary from a modern perspective, they represented a significant leap forward in their time, paving the way for future discoveries and advancements. The Aryabhatiyam remains a source of inspiration for scientists and mathematicians, reminding us of the enduring power of human curiosity and the pursuit of knowledge. Its historical significance, combined with its mathematical and astronomical insights, makes it a timeless treasure of scientific and intellectual history. Its very existence is a gentle reminder that even the most groundbreaking ideas often spring forth from fertile, intellectual grounds, built by the scholars of both past and present.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.